Okay. Good morning, guys and girls. Good morning, folks. It's nice to be back to our live system here. Let me fire up the .cam and we can get back to our usual thing. So this is MAC2312, section 002. This is a lecture, and today is the 26th. Today we're going to talk about alternating series. And there's two things there. There's the alternating series test, and then there's an estimation theorem. This is all coming from section 11.5. Let's see this guy, where he belongs. Okay, good. So today we're going to cover section 11.5, and then Wednesday we're going to cover section 11.6. 11.6 is the last section before the exam. So I am going to do something a little out of the ordinary. I'm going to go ahead and pop open the study guide today. And the reason is the exam Exam 2 is next Monday. Which is what we've been talking about before I went out of town. We mentioned that this was the most likely date for the exam, and then in some of those videos I recorded for you guys to watch last week, we talked about the exam being on that date as well. So there will be a little bit of material that you'll be learning between today and the test that is new, namely the root and ratio test. Section 11.6 you'll learn on Wednesday, which means you have a little less than a week after learning that new material before you're tested on it, but I feel like it's still a fair, reasonable amount of time. We're not moving inappropriately quickly there. But it is important that you're keeping up with everything from last week and the week before. We'll review for the test this Friday. I'm going to switch to that blue pen because my other pens are dying. All right. The exact content of the exam we'll go over during the review, but it's everything from exam 1 to now. So that's section 7.8, which was on improper integrals, 11.1 on sequences, and 11.2 through 11.6, which is all on series. So just so we're all up to date with the bookkeepy stuff, there it is. The material for today is about alternating series. So first we need to define what an alternating series is. Let me see, there's a question in chat. Sections on the test are 7.8 and 11.1 through 11.6 or 7, yeah. Technically through 11.7. 11.7 though is like 7.5, no new material. So if you're thinking like where are the theorems and formulas that you need to remember, they are from 7.8 and 11.1 through 11.6. All right, we say a series S is alternating if it changes sign, or if each term changes sign. For example, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. That would be an alternating series. Okay. These can be written as something like S equals sigma n from 1 or 0 or wherever to infinity, -1 to the n times bn, where bn is positive. Sometimes this will be a -1 to the n plus 1. Sometimes this will be a 0 instead of 1. But it'll always be a power of -1, or something that makes the thing alternate, times the non-alternating piece. The sum doesn't need to start at 1. It could start at 0 or at 3 or at 10. It could start anywhere. I don't care about where this number, what this number at the bottom is. And again, the power of -1 could be -1 to the n, could be -1 to the n plus 1, or -1 to the n minus 1. This is the piece that alternates. And then there's a positive piece. So the series in the example (1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. How could I write this in this form? This is sigma, because it's a sum, right? I've got a bunch of things added up. The stuff that I'm adding up looks like 1 over n, right? 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, that's 1 over n. But also we're alternating. So I've got a power of -1 here. I cannot start n at 0. My first term is 1 over 1. So if I'm going to write this as 1 over n has to start at 1. So we're going from n equals 1 to infinity. But then in order to make the signs match up, -1, I can't just have -1 to the n here, because -1 to the 1 would make this first term negative. -1 to the 2 would make this second term positive. So instead here, what I have is -1 to the n plus 1. Or you can write this more compactly as sigma n from 1 to infinity, -1 to the n plus 1 over n. So this is an example of an alternating series. Here, Bn is 1 over n. Any questions about the definition or the notation that we're using here? Are we all comfortable with why this is an alternating series? And how we could write it like this? Okay. Then I'll get to the convergence test. So far, when it comes to convergence tests, you have TFD, the test for divergence. You have the integral test, and you have 2 comparison tests. Your next convergence test is called the alternating series test. I'll flip back for just 1 second.
I had a question. This is kind of off topic, but when do our homeworks get like put into the gradebook?
Usually I don't enter the homework in the Canvas gradebook until the end of the term, but you can
Okay.
take your homework average in WebAssign and enter it as a what if score in the Canvas gradebook. If you haven't played with the what if options in the Canvas gradebook, I definitely recommend it. That's why I like that gradebook over others.
Okay, thank you.
No problem. Okay, so moving on. The alternating series test only applies to alternating series. So you can't use this on any other series, but it's very easy to use. I'll abbreviate it AST, just like I abbreviate test for divergence as TFD, and you're welcome to do so also. It says if S equals, let's say S is an alternating series with positive pieces Bn, and two things are true. First, the sequence Bn is decreasing, and the limit as n goes to infinity of the Bn's are 0, then the series S converges. That's it. So this is as close as a converse to the test for divergence as you'll ever get. And it's also probably the easiest of our convergence tests to use, but unfortunately it only applies to alternating series. Really quick, I want to mention that there are several ways to show a sequence is decreasing. Easiest way is it could be the reciprocal of an increasing sequence. Second, you could show that the derivative, Bn all primed, is negative. And the third option here is to show that Bn plus 1 is always less than or equal to Bn. Any one of these things will show you that, will prove that the Bn's are decreasing, and you have to pick one of them. If you go with the bottom one, you need to prove this for all n. It's not enough to plug in like 2 or 3 values of n and show, oh yeah, B2 is smaller than B1, B3 is smaller than B2, therefore the Bn's are decreasing. No, that's not correct. But if you can show that the inequality Bn plus 1 is less than Bn is always true, that suffices. If you take the derivative and show that the derivative is negative, that suffices. Or you can make that kind of lazy argument that we talked about when we learned the integral test. If your thing is the reciprocal of an increasing thing, then your thing is decreasing. Okay. So let's see if we can apply this. Let's investigate the convergence of that series from the start. Sigma n equals 1 to infinity, negative 1 to the n plus 1 times 1 over n. This is called the alternating harmonic series. because its first few terms are 1 minus 1/2 plus 1/3 minus 1/4 plus and so on, like we saw on the previous page. It's the alternating series, except it flips back and forth in sign from positive to negative, positive to negative. We've seen before that if you just had the 1 over n without the alternating piece, that is a divergent series, right? Without the alternating piece here, this is a p series with p equal to 1 and therefore diverges. We learned that when we learned the integral test. However, this series is alternating. So since S is alternating, we can use AST.
So what would be a key indicator that the series itself is alternating?
That it changes sign every term. Positive,
So,
minus, plus, minus. So if you're looking in sigma notation, having a power of -1, like -1 to the n or -1 to the n plus 1, that's a strong hint that the series is most likely alternating.
okay.
Or if you're uncertain, you can write out the first few terms and check that every other term changes sign.
Okay.
So we need to check two things. First, are the BNs decreasing? Well, here, what is BN?
One over n.
Good. So I could make the argument that n itself is increasing, so 1 over n is decreasing. Or I could say, and I want to show you how to do this at least once, Bn plus 1 is less than or equal to Bn. In this case, is equivalent to saying what? What is B sub n plus 1? What is this? If Bn is 1 over n, then B sub n plus 1 is?
B over n plus 1.
1 over n plus 1, yeah. So this is Bn plus 1, and Bn is just 1 over n. And is this inequality always true? Is 1 over n plus 1 always smaller than 1 over n? Well, let's take reciprocals on both sides. When you take reciprocals on both sides of an inequality, that flips the inequality over. So we get n plus 1 is greater than or equal to n. And this is certainly true. If you subtract n from both sides, this is equivalent to saying 1 is greater than 0, which is clearly true. So yes, the sequence Bn here is decreasing. All right. Of all the 3 ways to show that a sequence is decreasing, this is the one people mess up most often. So I just wanted to show you once how to do it. You need to prove that this inequality is true for all integers n. So you write down that inequality, and then you try to simplify it to something that is obviously true. If you insist on using this method to show that your sequence is decreasing, you need to be very careful. You need to make sure that your inequality work and algebra are correct. I'll say it one more time. Plugging in a few particular values for n here is not enough. Okay, alternately, you could have taken the derivative. The derivative of 1 over n is negative 1 over n squared. That is always negative. Or you could have said that 1 over n is the reciprocal of n, and the sequence n is clearly an increasing sequence, so 1 over n has to be decreasing. In any case, we're satisfied with item 1. Item 2, the limit as n goes to infinity of the bn's here is the limit as n goes to infinity of 1 over n, which is 1 over infinity, which is certainly 0. So yep, the bn's go to 0 as well. Therefore, by the alternating series test, the series S equals sigma n from 1 to infinity, -1 to the n plus 1 over n converges. In other words, the alternating version of the harmonic series is a convergent series. And this should start setting off some warning bells in your head. Right? The regular harmonic series diverges, but the alternating harmonic series converges. So somehow, alternating series have an easier time converging than series of positive terms. If you think about it, all of your convergence tests so far, except for TFD, except for the test for divergence, all the other ones require that your series have just positive terms. This is the first test we've had that allows for some of the terms to be negative. And maybe you can see how allowing some of the terms to be negative makes it easier for the series to converge, because rather than just adding more and more and more positive stuff, sometimes you're adding stuff, sometimes you're subtracting stuff, which makes it a little harder for the series to run away to infinity. I want to get a little bit more technical about this. I'm actually going to prove the alternating series test for you through a picture. But before I prove that, I'm going to show you the other theorem from this section because the picture actually proves both of them. So first, questions on this example.
So how did you go from, in the first section, how did you get that whole, the equals, the next equals the next equals the next?
This?
No, for the first part of the test.
How did I go from here to here?
Yeah.
Well, if Bn is 1 over n, then n plus 1 is 1 over n plus 1. So this is Bn plus 1, and this is Bn. So I'm just plugging in, what is this, and what is this? So the thing on the right there, Bn, I know is just 1 over n. And the thing on the left here, Bn plus 1, is what I get by swapping n for n plus 1 in this expression. So Bn plus 1 is this, and Bn is this. Are we good with this first piece?
Yeah.
All right. Then from here to here, I took reciprocals on both sides. I flipped both sides over. You can do that in an inequality. You're allowed to take reciprocals on both sides. That is a valid algebra move. You just have to remember to flip over the inequality also. So when I take the reciprocal on the left, the reciprocal of 1 over n plus 1 is just n plus 1. And the reciprocal of 1 over n is n. So if a is less than b, then 1 over a is greater than 1 over b. I just took reciprocals on both sides and flipped the inequality. And for the last piece here, I subtracted n from both sides.
Okay, I understand.
Cool. Yeah, so I can come in here and annotate. This piece is Bn plus 1, and this piece is Bn. So I just plugged in for the first step, took reciprocals for the second step, and then subtracted n in the third step. These are good questions. Other questions? Any other questions on this example here? Alex, the exam is going to cover up through 11.6. 11.6 is the last section with new material that is on the exam. Your study guide is going to be drawn largely from 11.7, which doesn't have any new material, but combines problems from the previous 5 sections. So the exam is 7.8 and then 11.1 through 11.6. And the study guide will come from 11.7. Think of 11.7 as the series version of section 7.5. Remember, section 7.5 is where we tossed all the integrals from chapter 7 together. So section 11.7 will be where we toss all the series from chapter 11 together. So the last section that has new material for the exam is section 11.6, which we will cover on Wednesday. All right, it doesn't seem that there are any more questions about that example, so I'm going to show you the estimation theorem, and then I'm going to prove both theorems for you.
Is there a definition for this one that we're
No.
gonna?
No, just the theorem. So alternating series still are what they are. I'm not going to redefine alternating series, because we've defined them already. But this says if S is an alternating series with positive pieces Bn, then S is an alternating series with positive pieces Bn, then S minus Sn is less than Bn plus 1, provided S passes the alternating series test. So if I hand you an alternating series that passes the alternating series test, then this inequality is true. And I want to explain that inequality a little bit. Remember here, S is the full series. I'm going to assume that it starts at B1. So it's B1 minus B2 plus B3 minus B4 plus B5 minus B6, etc. S1, the first partial sum is just B1. S2, the second partial sum is B1 minus B2. S3, the third partial sum is B1 minus B2 plus B3, and so on. And remember, there's 2 things that we know are true because we passed the alternating series test. The BNs are decreasing. And the limit as n goes to infinity of the BNs is 0. Okay, so here's going to be our proof. I'm going to draw a number line. I'll put 0 right here. And I'll say, okay, well, B1 is right here. And that's equal to S1. Right? Because S1 is just B1. It's the first partial sum. It's just that term left alone. How do I get from here to S2? Is S2 going to be to the left over here, or is it going to be to the right over here? Is the question clear? Good, it's going to be to the left because B2 is being subtracted. So if I'm here at S1, then to get from S1 to S2, I need to walk to the left by B2 units. So let me extend this guy's thingy up here. And we'll say we're going to walk left by B2 units. We're subtracting B2 to get from S1 over here to S2. Because S2 is B1 minus B2. And I know that I'm not going to go past 0 over into this space. Why? Well, because to get from 0 to S1, I added B1, right? And the BNs are decreasing. So the fact that the BNs are decreasing tells me that each step I take is going to be smaller than the step before. So I started over here at 0, and I walked to the right B1 units to get to S1. Then I walk back left B2 units, and I know that the distance I'm walking back left is smaller than the distance I walked right because the BNs are decreasing.
So I have a question. So if we were to do S3, this is just like visually, we'd go to B2, like subtract B2, and then we'd add a little bit to B3, so the next line would be in the middle between B1 and B2.
Very good. Yeah. So my next move is to add B3. That's how I get to S3, by looking where I am and adding B3. That'll plot me right here at S3. Ayushi, how do I know that I'm not going to go past S1 all the way to somewhere over here? How do I know that I'm going to be in the middle?
I am not sure about that one.
Is B3 bigger or smaller than B2?
Wouldn't it be smaller? Or no, bigger. It'd be bigger than B2, but smaller than B1.
Well, B3 is smaller than B2 because the BNs are decreasing, right?
Oh, yeah.
So that means that every term gets smaller and smaller.
Okay.
So B1 is the biggest term, and then B2 is the next biggest, and then B3 is the next biggest, and so on. So each of these arrows is getting shorter, and they point in different directions, right? They flip from one direction to the other. To get to S4, I would start here at S3 and walk back to the left B4 units. Yeah, so what you're gonna start noticing S1's over here, S2, S3, S4, S5, S6, S7, S8, S9, S10. They're gonna start piling up in here. You're gonna bounce back and forth, and you're gonna start converging towards one particular number in the middle there, and that is the full series S. This is it, this is the picture, this is the proof. Because the BNs are decreasing, you're always walking in. Right? I go right, then I go left, but I go left less than I went right. And then from here, I go back to the right, but less than I went to the left in the previous step. And then from here, I go back to the left, but less than I went right in the previous step. That means that we have to be coming in. That comes from the BNs being decreasing. Now it's possible if the limit of the BNs was not 0, that I would end up flipping back and forth between two positions out here. But because the BNs are decreasing, I'm coming in. And because the limit of the BNs is 0, this gap has to narrow to 0, right? The gap is BN. So if this gap is narrowing to 0, then I have to come into a single point here. That's it, that's the proof. This picture is in your textbook. And then the textbook offers a somewhat more rigorous proof by splitting the series into even and odd parts. I'm not a big fan of that proof. It's okay. But really the trick to understanding this stuff is to understand the picture. I want to say a little bit more. But first, any questions about why this picture proves AST? Why it's the case that if the BNs are decreasing and have limit 0, then this result must end up centering at some point here. It's fairly intuitive, right? The picture in the textbook is here. It's a little bit more clear. They've got more space when they typeset things like this. It just looks prettier. But that's it. So you jump right, then you come back left a little less. Then you go back to the right, but less still, and then back to the left, but less still, and then back to the right, but less still, and then back to the left, but less still. Which means this back and forth hopscotch game where you're shrinking in has to eventually shrink into some central point. And that is the value of the series S. Now, I claim that this picture also proves the estimation theorem. This expression right here, this is the distance from Sn to S. Remember, the absolute value of the difference of two numbers is their distance along the number line. Like the absolute value of 3 minus 10, well, that's the absolute value of -7, that's 7. And if you look on the number line, the distance from 10 to 3 is 7. Another word for this distance is the error in Sn. We're asking how far is Sn, the nth partial sum, from S, the value of the full series. And what this theorem guarantees, oh, I think this should be a less than or equal to, sorry, less than or equal to. What this theorem guarantees is that the distance from Sn to S, the distance from the nth partial sum to the full series, is no greater than the next term. And if you look at this picture, you can see why that is true. Let's say I want to find the distance from S2 to S. That's this distance right here, the distance from S2 to S. Notice that the next step from going from S2 towards S is to jump all the way over S to S3. Because S is in the middle between S2 and S3, the distance from S2 to S is less than the distance from S2 to S3. But the distance from S2 to S3 is B3. So the distance from S2 to S is less than B3. The distance from S2 to S is less than B3. That's exactly this inequality with n equals 2 plugged in. Or if you want to look for the distance from S3 to S, the distance from S3 to S is less than B4 because S is in between S3 and S4. I have to jump over S in going from S3 to S4. But the distance from S3 to S4 is B4. So the distance from S3 to S is less than B4 because B4 takes me all the way over here, but the distance from S3 to S is just this little distance. So because you jump over S every time, the distance between any partial sum Sn and the full sum S is always less than the next term. So this picture really proves two things. It proves the alternating series test and the estimation theorem. It's a beautiful picture. I'd like to now show you how to use the estimation theorem, but before I do that, are there any questions on what this picture is trying to communicate? Okay, let's do it then. Let's use this. Use the estimation theorem for alternating series. I'll just write alt series to approximate the value of that alternating harmonic series, the one that we already showed converges, accurate to 3 decimal places. I actually know what the exact value of this series is. I can tell you what the exact value of this series is. It's the natural log of 2. And you'll be able to show that and lots of other stuff like that after we've talked about power series. But for now, we don't know that. If I want to approximate this series accurate to 3 decimal places, the idea here is to find, so i.e., what we're trying to do, find the smallest n, smallest value of capital N, such that Sn is close to S, correct to 3 decimal places. In other words, I need the error, which is S minus Sn, to be less than 0.000. This guarantees that the first 3 decimal places are correct, and then I'll put a 1 here. So another term for this distance is the error. It's how far Sn is from the actual value S. That distance can be thought of as how wrong Sn is when taken as an approximation for S. Okay. So how do I do this? Well, I know by the theorem S minus Sn in absolute value is less than or equal to B sub n plus 1. Therefore, it suffices if I know that this is smaller than this, and I want this smaller than this, I can just solve this is smaller than this. All right? If Billy is shorter than Sammy, and Sammy is shorter than Sally, then Billy is shorter than Sally. It suffices to solve this inequality. I know that the distance from S to Sn is always smaller than Bn plus 1. So if Bn plus 1 is smaller than 0.0001, then S minus Sn will be smaller than 0.0001. That inequality is equivalent to saying B sub n plus 1 is less than 0.0001 0.001 is 1 over 10,000. What is b sub n plus 1? I know that bn here is 1 over n. So what is bn plus 1?
Can you repeat that?
So the right-hand side of this inequality is 1 over 10,000. What is the left-hand side? What is bn plus 1? What goes here?
1 over 10,000 plus 1.
What is bn?
Mm,
For this series, what is bn?
1 over n, so that side would be 1 over n plus 1.
Good. B sub little n is 1 over little n. So b sub big N plus 1 is 1 over big N plus 1. Right? Just like function notation. So this is 1 over cap N plus 1. So this is the inequality that I need to solve. Good. Yeah, this is not a hard inequality to solve. You can take reciprocals on both sides and you get n plus 1 is greater than 10,000. And then you can subtract 1 from both sides to get n is greater than 9,999. There we go. In other words, S9999 is very, very close to the actual value series S. So then I wrote 0.001 as a fraction. 0.001 is 1/10,000th. This piece is literally 1 over 10,000. Just wrote it as a fraction. All right, so because this inequality is satisfied if n is at least 9,999, then I know that the 9,999 sum is a good approximation for S, accurate to at least 3 decimals. Let's do the computation. I told you that S here, the actual value of this series, is the natural log of 2. Let's see what S sub 9999 is equal to. Sorry, ignore this little squiggle here. We don't need this. We want to use something like this. So here our sum is -1 to the n plus 1, all divided by n, from n equals 1 to n equals 9999. All right, so I get 0.6931197 blah, blah, blah. What's the actual value of the natural log of 2? It's 0.69314 71 blah, 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 blah. So did we do the job? Well, the 9,999th partial sum of my series, which is something we can compute exactly because it is finite, has decimal representation 0.6931197. The actual value of that series is the natural log of 2, which has decimal value 0.6931147. So not only are the first 3 correct, the first 4 are correct.
So
Good precision.
on
Yeah.
the exam, if we were given a question like this, and you said to round to 3 decimal places, would we have to find like the sum of the first 9,999 numbers?
I usually ask a good question. So you guys saw me, I used Wolfram Alpha to compute this thing because I don't want to add 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 all the way out to 1 over 9,999. On a test, this would go one of two ways. Either I would just ask for the value of n and not ask you to do the computation. That's an option. I could say, what is the smallest number n such that this series is accurate to 3 decimal places? And then you could stop here. You could say any n greater than or equal to 9,999. Or I'll use a series so that the solution here is much simpler, right? Not as long. In fact, the second example I have planned for you today is going to go a lot faster. There is some take-home stuff. So first, Ayushi, did that answer your question? Are you comfy with that?
Yes.
All right. Yeah. So in practice, if I make you do this exact thing on a test, you won't be using S sub 9,000. You'll be using S sub 5 or something like that. There's a cooler thing to look at here, and it's kind of talking about the speed of convergence. When we've talked about infinite series in the past, I mentioned that the tail is what determines whether the series converges or not, right? I don't care what the first finitely many terms of a series do. What determines whether the thing converges or not is what the series behaves like as n goes to infinity. Some series converge very fast. Some series converge very slow, meaning the tail might get small very, very quickly. That would be converging fast. Or the tail might get small very, very slowly. This series, the alternating harmonic series, converges very slowly. That's why you needed so many terms in the series to get an accurate decimal representation. The first 5 terms of this series are a horrible approximation for the actual value. You had to go all the way out and take the first almost 10,000 terms to get a decent approximation. But there are other series which converge much faster. So another famous example like this, and we're going to go through the whole thing here. We're going to show that the series S equals sigma n from 0 to infinity, -1 to the n over n factorial converges, and then approximate its value, again, accurate to 3 decimals. I could say, you know, with an error less than whatever, and that would be a similar sort of problem, right? If I said with error less than 0.05, then you would have the same sort of setup. So I've got 2 things to do here. I need to show that the series converges, and then I need to use my estimation theorem to approximate the series. What sort of tests could I use to show that this series converges? Don't think too hard. Anybody?
The alternating series test?
Yeah, that's the thing we just learned, right? So S is an alternating series. It's 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus, and so on. It's an alternating series. So let's use AST. Let's use the alternating series test. What are the BNs here?
1 over n factorial.
Very good. Right, because I could write this as -1 to the n times 1 over n factorial. The non-alternating part, the positive part of my summand, is 1 over n factorial. So I need to answer two questions about these. Are the BNs decreasing? And is the limit 0? First, are the BNs decreasing? How would you guys like to show this?
Wouldn't they be decreasing? Since I'm thinking of the picture, but that's just me.
Well, so I need to show that the BNs are decreasing. Remember, with the alternating series test, we have to show that these two things are true, and then we can conclude that the series converges. So if you're thinking about the picture, that picture is for a series that we know passes AST. We don't know that about this series yet. So we don't know if this picture, if that picture applies to this series. That's the thing. So we have to show that that picture applies to this series. Then we can use the theorem. To show that the picture applies, we need to show that the BNs are decreasing and have limit 0. So how could I show that these BNs are decreasing?
Well, since n factorial is increasing, isn't it?
Very good.
Will
Yeah.
increase.
I would say we know that n factorial is increasing. We know that because we've played with the factorial function quite a bit, right? We've looked at its graph. We know that as n gets bigger, n factorial gets bigger. So its reciprocal, 1 over n factorial, must be decreasing. Or we could take the derivative, but here the derivative of n factorial, the derivative of 1 over n factorial, is very complicated. It's not an easy thing to differentiate. I'm going to show you something cool really quick. On one of your old homework assignments, do you guys remember when I made you mess with this thing? One of your integration by parts problems had you show that for different values of n, this thing comes out to different things. This is called the gamma function, and it's another way of writing n factorial. If you want to take the derivative of n factorial, this is the way you do it. First, you write the n factorial in terms of the gamma function, then you differentiate through this with respect to n. Very complicated. So we don't know how to compute the derivative of n factorial. It's hard, because you have to use this thing. So we're not going to do that. What's the other option? How else could we show that this is a decreasing sequence? We've already shown it, just to be clear. What we have here, n factorial is increasing, so 1 over n factorial is decreasing. That's good, we're done. But just for practice, I want to ask, how else could we have shown that this is decreasing?
Show that b of n plus 1 is greater than or equal to b of n.
Almost. We want to show that bn plus 1 is less than or equal to
Oh,
bn.
sorry.
Yeah, right idea. No, and I'm sure if you wrote it down, you'd write it correctly. We want to show that the next term is always smaller than the previous term, right? So as the subscript gets larger, the overall output gets smaller. So if I were to plug in here, bn plus 1 is 1 over n plus 1 factorial, and bn is 1 over n factorial. And what would I need to do with this inequality in order to conclude that the BNs are decreasing?
Take the reciprocal of each side and then
Yeah,
solve for
We
n.
want to reduce this inequality to something that we know to be true. And the first step in that is just what Ayushi was saying. We want to take reciprocals on both sides, which would give me n plus 1 factorial is greater than or equal to n factorial. Okay, what could I do from there?
Could you solve for n?
Yes, how?
Is it possible to cancel out the factorials?
Unfortunately, no. So the factorial function is not a simple function. I can't like undo the factorial in any easy way. It's not like a square where you can take square roots. But I can write them out. I know what n plus 1 factorial is. It's n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. This is n plus 1 factorial. Do we all remember the definition of the factorial? You take whatever number is being factorialed and you multiply it by all the things less than it down to 1. And similarly, n factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And now if you divide both sides by n and n minus 1 and n minus 2 and all the numbers down to 3 times 2 times 1, you get n plus 1 is greater than or equal to 1. So I'm going to divide both sides by all of this. When I divide both sides by the red underlined quantity, the only thing that's left on the left is n plus 1. And the red underlined quantity here is exactly the whole right-hand side. So I would have n times n minus 1 times n minus 2, blah, 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 all divided by n times n minus 1 times n minus 2, blah, blah, blah. That's 1. And is n plus 1 obviously bigger than 1? Yes, it is. If you want to be silly about it, you can then subtract a 1. So this would be the other way to show that the BNs are decreasing. You probably see why I prefer the first way. First way is much easier. But you need to actually make sure that your thing is the reciprocal of an increasing sequence. So here, we do know that n factorial is increasing. 1 over n factorial is therefore the reciprocal of an increasing function must be decreasing. It's easy. The third option of taking the derivative, like I said, really not something we can do here because we don't know how to differentiate n factorial. So the net result is a big checkaroo. Yeah, these things are decreasing. What about the limit?
Doesn't the limit approach 0 as it approaches infinity because the denominator is getting bigger and bigger?
Yeah, good. This is the limit as n goes to infinity of 1 over n factorial. Since n factorial goes to infinity as n goes to infinity, this is 1 over infinity, which is 0. So that's a checkaroo there as well. Thus, by AST, hence, by the alternating series test, our series S equals sigma n from 0 to infinity, negative 1 to the n over n factorial must converge. Okay, so we have the convergence. But what I don't have is an approximate value for the series. Any questions on the convergence result here before I move on to using the estimation theorem? We all comfy with this? Okay then. The next thing we're going to do is approximate my series. So now we want to approximate S accurate to 3 decimals, which means we want the error less than 0.0001. That's the same as saying that we want S minus Sn in absolute value to be less than 0.0001, which is guaranteed provided Bn plus 1 is less than 0.0001 by our theorem. So the wording here you want to pay careful attention to. It's a little bit subtle. Remember, the absolute value of S minus Sn is the distance from the nth partial sum to the full series. So that is your error. We want that error to be less than 0.0001, then that's the same as saying we want absolute value of S minus Sn less than 0.0001. And our theorem, our estimation theorem, guarantees that the error is always smaller than Bn plus 1. So this will be smaller than this as long as this is smaller than this. Always the inequality you're going to end up solving is Bn plus 1 is less than whatever the allowed error is. Maybe we should make a note of that. We always end up solving the inequality B sub n plus 1 is less than the specified error. So here, what does that inequality look like? What is Bn plus 1? Bn is 1 over n factorial. So B sub capital N plus 1 is 1 over capital N plus 1 factorial. Thus, our inequality we must solve 1 over n plus 1 factorial is less than 0.0001. And now we get to the actual solving. That's the same as saying 1 over n plus 1 factorial is less than 1 over 10,000, which is the same as saying n plus 1 factorial is greater than 10,000. And again, we run into this issue of the factorial function being hard to work with. There's no way to like undo this factorial and get n alone. It's the same problem we had when we were talking about the decreasing stuff earlier. It's very, very hard to get rid of a factorial. So to solve this inequality, what we actually do is we're going to guess and check a little bit. I know you might not have heard that phrase since second grade, and I apologize for bringing it up in a calculus class, but that's really the only way to do it. So from here, we guess and check. I know what 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial are, and none of them are bigger than 10,000. So let's start at n equals 4, just for fun. When n is 4, n plus 1 factorial is 5 factorial. That's 5 times 4 times 3 times 2 times 1. That's 120. When n is 5, n plus 1 factorial is 6 factorial, is 6 times 5 times 4 times 3 times 2 times 1. That's 720. I'm going to stop writing these out now, but when n is 6, then n plus 1 factorial is 7 factorial, which is 7 times this is 5,040. And when n is 7, n plus 1 factorial is 8 factorial, which is bigger than this. Somewhere, I did this calculation earlier. Yeah, 40,320. So n equals 7 is the first guy that works. N equals 6, not big enough, because n plus 1 factorial there is about 5,000. 5,000 is not bigger than 10,000. But when n is 7, n plus 1 factorial is 40,000. So this will be true if n is greater than or equal to 7. In other words, the 7th partial sum here does the trick. S7 should be correct to 3 decimal places. Well, what is S7? It's 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial minus 1 over 7 factorial. Right? That's what S7 is. And I'm not going to do this computation by hand, but we can borrow our friend Wolfram alpha to sum -1 to the n over n factorial from n equals 0 to n equals 7. So here it is. If you compute that, it's 103 over 280. I'll write this down and then come back to the dot cam, which as a decimal is like 0.3678571, and so on. The actual value of the series S here is 1 over E. I'll be able to prove that to you after we've learned a little bit about power series. Yes, Alex, your question there, the answer to that is yes. It is always the case that to go from one factorial to the next, you multiply by the next number. And that comes from the definition of the factorial, right? 6 factorial is 6 times everything smaller than 6. 5 factorial is 5 times everything smaller than 5. So there is a copy of 5 factorial hiding in 6 factorial. So to get 6 factorial, just multiply 5 factorial by 6. Similarly, to get 7 factorial, you multiply 6 factorial by 7. Yep, if you remember, that's actually how we introduced the factorial function as a recursive sequence, where to get the next term, you multiply the previous term by the next number. So yeah, your answer to your question is yes. Now to finish up our example here, we've got S7. S7 is 103 over 280, which has this decimal approximation. Using power series, I can prove to you in a few weeks that the actual value of this series is 1 over e. What is 1 over e as a decimal? 0.367879. So, coming back here, how'd we do? Did we get the first 3 decimals correct? Yeah, we got more than that. Look, the actual thing here is 0.36787, and here we've got 36785. So the first 4 decimals are correct. And in the 5th decimal place here, we're off by 2 units. So we are off by less than 2 10,000ths. Solomon, that's another question entirely. So what we will be doing after exam 2, we're going to continue working with series, but we're going to start working with what are called power series. These are series that have a variable in them. They end up looking like infinitely long polynomials. Turns out it's not very hard to build a power series for the function e to the x. And the way I know that this series is 1 over e is by taking my power series for e to the x and plugging in x equals -1. Now there's a lot to that, and that's all coming after exam 2. So don't stress about that for now. Just like how the previous series I knew had value natural log 2, this series I know has value 1 over e. That is not a part of what you're responsible for on exam 2. You will learn it and need to do it on exam 3, but for now, you guys don't know how to get that stuff. The only reason I'm mentioning it here is so we can compare the exact value of this series to the approximation we get from our theorem. So are there any questions as to how you would do this on a test, or what's expected of you when you encounter these in the homework? Alrighty then. I think that is where we're going to end it for today. That's all of section 11.5. On Wednesday, we're going to talk about 11.6, which is on the root test and the ratio test. Now you have, oh yeah, Solomon, go ahead. What was the question? I used Wolfram Alpha to sum these. You could have had a common denominator and written these all out by hand if you wanted to, but I just used Wolfram Alpha to sum them. So on a test, you could just tell me S7, right? On a test, you would end here. I did these, and you ought to as you do the homework problems. There's only one homework problem that has you do this. You should go ahead and crunch these out, and you can use a tool like Wolfram or whatever you like for calculating sums. But on a test, I'll either make sure that this thing, the thing you have to crunch, is very, very small and easy to work with, or I'll tell you to stop at this step. All right, so you've got homework to be working on. There's a new homework that just opened for this week, and there's the homework from last week, which I imagine, some people are not yet done with. I'm going to go through and clear out all the extension requests right now. And then I would like you guys to make sure you're working very, very hard on these homeworks. Remember, this is the part of the class that fucks people over. This is the part of the class that gives Calc 2 the reputation it has. These concepts are challenging, and do not bullshit yourself about how challenging they are. Talk with one another, talk with me. I think we went through the process of ensuring that there's a group me or a Discord or something for this class. I'm happy that those things exist. Don't use them to cheat. Do use them to talk with each other about your solutions. Please be communicating your solutions with each other and with myself so we can verify that your logic is sound. Yeah, so has anybody started a GroupMe or a Discord for this class? If not, I can start one. I don't think you guys want me in there. So I'd be fine if you started one on your own. Has anybody started one of those things for this section? You don't have to tell me what it is, just say yes or no. Sergio, yeah, that's right. Sergio had started one. And I think he sent it out to pretty much everybody last time we had a face-to-face meeting or whatever, a Zoom meeting. So yeah, message Sergio, he will add you to whichever that thing is. Get in there, be talking with each other, and if you have solutions that you're unsure about at all, send them to me and I'll give you guys feedback. Make sure you're grinding really hard. This test is gonna be hard. And I want you guys to do well. So make sure you're preparing. I'll go ahead and pop all those homeworks that anybody requested be opened. And then I do have a normal office hour this afternoon from 3:30 to 4:30. All right, take care guys. I'll see you next time.